In this video, we're going to be talking about how to interpret the results of a Kaplan-Meier survival curve when analyzing the results of a journal article. Now, Kaplan-Meier is one type of survival analysis. Survival analyses are commonly used in the literature. The other major type is the Cox proportional hazards ratio. This uses more principles of regression and time, where Kaplan-Meier focuses heavily on time to event data. Now, although the name is survival analysis, it doesn't necessarily have to be death that's collected. It just has to be an event that occurs one time, like rejection of a kidney transplant. Another important thing is that data must be collected for all patients, and if patients drop out or leave, they have to be censored. Now, censoring is usually a negative word, but what this means is that we only use part of that patient's data within the survival analysis, and what we'll do is we'll go through an example showing you what goes into making a survival curve. And in this example, we're going to be using Dr. Giuliano's multivitamin, and we're going to be looking at survival over time in patients with metastatic cancer. So we're going to enroll patients from 2015 to 2017, and then we'll follow them all the way up to 2025. Now we're going to pretend that we're at the end of the study, and we're going to use the patient data to see the survival for patients on Dr. Giuliano's multivitamin. Notice that we're only looking at Dr. Giuliano's multivitamin, and there's no control at this point. We'll go over how to compare it versus a control later. So the patients that we had in the study, the first death that we had was at 2 years. The third year, we have a patient that moved out of state. This little C with the circle means that we censor them. And again, we're going to be using part of that data, and then you'll be able to see mathematically how we use part of the data, but then eventually we lose the patient. At 5 years, we have our next death. 6 years, we have a death but from a car accident, and this is likely not something that would have been caused by the multivitamin. So we censor this also, and we use all the data up until they died, but we don't actually count them as a death because it's not necessarily related to the medication that we're studying. Now, we're only going over a few patients in this data set, but clinical trials are going to have thousands of patients, and they'll use computer programs to do what we're doing now. But this will help you understand the magic behind the survival curve. Next, we had a patient at 7 years after enrollment. They passed away. And then we had 2 patients, one alive after 8 years and then one alive after 10 years at the year 2025. So those patients were alive. At that point, their data becomes censored because we don't continue to follow them after 2025. So we don't know when they end up passing away. We just know they were alive the whole period of time in the study. Now we have enough data to construct a Kaplan-Meier survival curve. Now, to create the survival curve, we're going to need to calculate specific points to construct this. The points are calculated using the equation, and the equation is the number of patients alive at the end of the day divided by the number of patients alive at the start of the day. So if we start at our first data point, we can see that we have a total of 7 patients, and At 2 years, 6 are alive at the end of the day versus 7 are alive at the start of the day. And so our first point will be 85.7%. Now it's important to note that we do start at a baseline of 100%, and our first point is 85.7%. Now our next patient moves away. So we censor them, but we use the data for a while. When we censor, we subtract 1 off the numerator and the denominator. This will help us out when we get to our next patient. So our next patient passes away at 5 years. So we have 4 patients alive at the end of the day and 5 at the start. Now we multiply the 4/5 times 6/7 to get our cumulative survival, which is going to be 68.6%. Our next step, we have another censored patient, so we go from 4 out of 5 to 3 out of 4, and then we go to our last patient that passes away, and so we have 2 alive at the end of the day and 3 at the start. We multiply by all of our fractions again, and we get 45.7%. Now, let's draw this out into what a survival curve looks like. So we start with cumulative survival on the y-axis with time on the x-axis. And everybody starts at 100%. And then we have our first drop off at 2 years. And then we have our next drop off at 5. And our final drop off will be at 7 years. And so at the end, we get to 45.7%. Now we need to put in where our censored data was. We'll make little green slashes to indicate this. So there was 4, counting the 2 at the end of the study. The next thing that you may want to look for is a 95% confidence interval. Because we're drawing these out, we won't be able to calculate that, but there should be one in the paper itself. Another important piece of information that we can get from this graph is the median survival. We usually don't calculate mean survival because it requires no censored data, but calculating median survival is pretty easy to do. You just need to find the point where 50% of the patients were alive and draw a line straight over to that. We'll do that with a green line here. And so it's around there, and that comes to be around 6 years for the median survival. Another useful thing to look at is the 5-year survival rate. This time you'll want to find the time of 5 years on the x-axis and draw up to the y-axis until it intersects the line, and that will be your 5-year survival. And we know that our 5-year survival in this study was 68.6% because we already calculated that. Now let's go over the assumptions of the Kaplan-Meier. So the first one is that the sample needs to be random or representative of the population that you're studying. The second assumption states that the samples need to be independent. So one example of a non-independent study would be using patients from a sick hospital and using them more frequently than patients from a less sick hospital, because you're going to get a population that looks more like the sicker hospital, and then your survival curves are going to be worse. Now, the next one is the endpoints need to be consistent. So when you defined death, like in a car crash, we said it didn't count in this case. You have to be consistent throughout the study. You can't change the criteria. Also, entry criteria for the study need to be consistent and cannot be changed. The start time of the study needs to be clearly defined. One example of a poor way to do this would be to ask a patient to remember the first time they had symptoms of a disease, rather than looking at when they were diagnosed with a disease. Because if a patient is trying to remember, they might have trouble and you might get a heterogeneous answer. The next assumption is that censoring is unrelated to survival. So what we don't want to happen is a patient essentially drops out of the study because they're feeling worse, or their doctor removes them because they're not doing well. You lose the outcome of survival in this case when it could have been due to the intervention. Lastly, the average survival cannot change during the study. One example of how this could happen is if a new drug comes out that treats the disease that you're also treating that vastly improves survival. This could change patients' survival throughout the study that isn't dependent on the drug you're studying. Now, most of the time in the pharmacy literature, we're interested in looking at least two survival curves. So we like comparing drugs or medications. The additional assumption that you get when looking at two groups is that you do need to define the groups before the data is collected. So just make sure you do that before the data is collected. And now let's look at a picture of survival curves, two survival curves. So again, we have cumulative survival on the y-axis with year on the x-axis, and we'll draw out potentially what Dr. Juliano's multivitamin effect is over time. And now we will draw out a comparator, a placebo potentially, and we'll see what their survival is like over time. And we can see that these two curves are different. They're not intersecting, but we need to describe them. So the question is, how can we describe these curves? One way we can describe these curves is the hazard ratio. The hazard ratio compares the steepness of the curves against each other. If the curves are identical, the hazard ratio is 1, and it's important to look at the 95% confidence interval. If the 95% confidence interval does not cross 1, then the hazard ratio is statistically significant. Now, if the hazard ratio is 0.8, it means patients in the treatment group are dying at 80% of the rate of the control group. This interpretation behaves similarly to relative risk. Now, another thing that we can do to compare these two curves is look at the ratio of the median survival time. And we can do this by looking for the 50% point on both lines. So we draw a straight line across at 50%, and we look at the ratio between those two green lines that are vertical. We can also compute a 95% confidence interval for the ratio of median survival as long as the ratio is consistently different over time. Lastly, we could calculate a p-value. The null of this test would be the survival curves do not differ. And the specific statistical test that we would use would be called the log rank test. And you'll get a p-value or a probability value that tells you if you can reject the null hypothesis. Again, we'd be looking probably for less than 0.05. Now, lastly, data with the Kaplan-Meier can be analyzed in two different ways: the intention to treat, using all the data, including the censored data, and then the per protocol, which only uses a part of the data and excludes patients.